Okay, so 3.10.1, doing musical note frequencies. So this is, got the Chorus simulator open here. The idea is that if the input is 440, then the output should look like this. So what we're doing is we are basically taking A above C, and if we start with that frequency, we should output that frequency and then the frequency of the next four notes on the piano. So A sharp, B, C, C sharp, and D. Actually, I guess we end at C sharp right here at 554. So basically, what we're going to need to do that is a formula for figuring out what the distance between one note and the next is. And this is sort of, first of all, it's starting with an input, so it's contingent upon the input it being an actual note itself. Obviously, if we put in like 445 hertz, we would end up with numbers that, yes, they would be half steps from there. However, it would not be a note that you could actually hit on the piano unless your piano was slightly out of tune, the entire thing. Slightly off pitch. It's kind of like when you sing and you're trying to hit the A note and you don't quite hit an A sharp. You're close to the A, but just off. In the West, we've taken an octave, which is the repeating sound, the sound that repeats itself at a higher frequency. In fact, double the frequency. So this is 220 hertz. This sound wave, it looks like that, happens 220 times a second. This one happens 440 times a second. And that one happens 880 times a second. So we've taken the space in between that and we've cut that into 12 distinct sounds, all of which having sound-wise equal distance from each other. So the change in pitch from here to here is the same as change in pitch from here to here, and it's also the same in change in pitch from here to here. Right? So we call those half steps, and we've basically divided the space in the octave into 12 parts. And those 12 parts are indicated by all of the keys leading up to the next one. So the white keys make up do, re, mi, fa, sol, la, ti, and then do again, right? Or starting with middle C, because it has no sharps or flats in the major scale, which is what the piano is based off of. It goes C, D, E, F, G, A, B, C. And we've put half steps in between the notes where there is a note in between what's in the major scale. So we end up with a half step to C sharp and then a half step to D. So the major scale consists of a whole step, a whole step, a half step, a whole step, a whole step, a whole step, and another half step. That's the major scale. The 12 steps in that same octave would sound like this. Right? Anyway, so what we're trying to do is pick any note on the piano and output that frequency and then the next four. So that's the purpose of this. The mathematical equation to figure that out, because if this is 220 and this is 440, if this is 220, this is 440, and this is 880, then obviously mathematically the space in here, the interval between there frequency-wise is going to be twice the interval here. So 440 to 466.16 and change in the case of 220 hertz, it's going to end up being 233.08 and change to get that same sound, equal 1/12 of the octave sound. So basically we're taking 2 to the 1/12, and that is the space that's between any note and the note next to it. Likewise, the negative of this would take you backwards. So then, in order to get the next notes, we start with a base frequency, we multiply that by this to the power of however many steps away we are. So that's what we're doing here. So we know that we're going to need to have a float frequency. We know that I'm going to use a float R for this R here. And mathematically, I don't know why they call that R and why they call it N. N, I guess, is probably just the, it's often used in math for the nth time something happens, right? Or the nth space, step away, the nth half step away, I should say, the nth 1/12 of an octave step away. So then I guess we'll use an integer for that, and I'm just going to call it steps. All right, and then we also, so we know that we want to come up with an R is equal to R to the 1/12 power, and then we know that we want to come up with the next frequency is equal to the current frequency times R to the steps away power, right? R to the steps away power. So in order to write this out in Coral, we would do R equals, and we would use the raised power, the built-in. We could write our own function, but don't really we don't really need to do that, right? Because we can just use the built-in function. So we're going to take the built-in function, and we know that we then put a comma in between instead of the caret here, and we can just put that, or we could put that to make it a little bit more clear, well, easier to read. So that's R. And then we know that we're going to end up using this for each next frequency. So what we would probably want to do here, we can go ahead and do a put current frequency to output, but the current frequency, we don't have that yet, so let's do frequency equals get next input. So now we've gotten our input, put frequency to output, we need a space, then we can start with our, now we know that we are caret steps away, R to the steps away power, we're going to do raise to power, and then we're going to do R, comma instead of caret, and then put our steps, and we're going to put that to output, and then a space to output. Now, this current step, if we're just doing it at this point in chapter 3, we hadn't, I've already gone through the whole course, so I did that, just kind of powered through it as fast as I could, and now I'm going back and doing all this. So at this point, we actually hadn't learned yet about loops. So we were learning about if statements and conditional statements and code branches and selections and stuff. So basically, the way that this would be done is it would have a, instead of steps, we would just do one step away, because in this case we're just one step away. And then the next one we would put frequency times raise to power R 2 steps away to output, put another space, and then R 3 to output another space, and then we would do our final final one right there, and we can get rid of this, and we can get rid of this, and we can get rid of our integer steps. We don't actually need that right now. So this will be our code. When we run this, we should get an output. Whoops. This is Coral, and in Coral, when you do division with two integers, the result is the integer, and so what it's giving you is it's giving us 440 times. First of all, this should not be r. R is a 0 at that point, so it should be a 2. But even if we did it as a 2, it's going to give us the same output, because what's happening is we're not getting anything. This is 0. Because if you do in integer math, let's just start it out here. And let's do put 1 divided by 12 to output. In integer math, what that gives us is a 0. So effectively, we're running these changes 0 times. So it's, we're just going to get, it's just going to be itself. This is going to evaluate to a 1. And so basically, we're just going to do frequency times 1. Frequency times 1, frequency times 1 is the math of what's going on there. So we need to force this to do float division. So we'll do 1.0. This will give us a float, and that should give us the values that we're looking for. And there they are, and it wants them spaced out, which they are. It's just the way that this is done, it doesn't look like they're spaced out. So this code would itself work. We can see the flowchart is just sequential code. However, we can go ahead and using what we learn later on, which is kind of what I like to do as I'm going back here, is just kind of make everything a little bit more efficient. What we can do is we can go back and we can say we can do it for, and for this I will go ahead and I will use an integer steps, and of course I could use a count. I could just use an I here, but for steps equals 0, and then steps is less than 5. Steps equals steps plus 1, and then I will tab out, and I'm going to get rid of 2 of these. And then we're going to do this, and in here we're going to put steps. So steps is going to start out at 0, so this is going to do the first one, and then when steps goes to 1, it'll do r to the 1, then r to the second power, r to the third power, r to the fourth power. When it gets to 5, 5 will no longer evaluate to be less than 5. Less than 5 will no longer evaluate to be true, unlike the 4 is less than 5, 3 is less than 5, etc. So it won't run any of this code. However, if we do this, the output did not ask for a space at the end. And if we do this, it will leave us with a space right here. So in order to get rid of that space, timeout. We would just come over here and do an if steps, and we could do here is not equal to 4. So when steps equals 4, that's the last time, and then we could go ahead and do that. And now we've got all the frequencies still accomplishing the same thing. Much more efficient code, and it would be very easy for us to change this now to, for example, show, if we wanted to show all of them, we could just do this, and for example, maybe we want to go ahead and stick them on separate lines. So here we get 1 full octave, including the original note 1 octave higher. So what we have here is A sharp, B, C, C sharp, D, D sharp, E, F, F sharp, G, G sharp, and back to A. So this is in the case of 440, that's what we get there. Now, in the case of 220, we can see here, we're still getting 1 full octave. And like I said earlier, this is half of 466.163 and change. We've got 233.08 and change. And multiplying by this number, right, is going to give us the proper step, right? And because it's a 1.05, it's always going to be dependent on whatever's before it. So theoretically, we could also just take this number here and say, let's just put in right here. Now, we can do it this way, and we get the exact same output. Gets us right up to the next octave. So we didn't necessarily need to use this, but they were trying to get us to learn this. We also could have put this raised to power, this whole line right here, we could have put in place of this R right there and never not even used a variable, or just put this in here and then our steps variable. So that is the code there. This is the equation. The answer to this being all of this right here equals 1. And that kind of shows you, sorry, this shows you why earlier it was just showing 440, 440, 440, because if we multiply 220 and we don't do the float math here, we just do an integer. Integer math takes the decimal and everything to the right and throws it out. So what you're left with is just the 1. So 220 times 1, and so on and so forth. So that is why it was all just 440, and it would have been all the same, because it would evaluate this whole statement to just equal 1. So you'd just be multiplying no matter how many times you raise this whole thing or this number here to the power, to the first power, second power, third power, fourth power. If it's only a 1, 1 to the 10th power is still 1, because it's just 1 times 1 10 times, right? So, all right, so that is that. And now I'm going to step over to my code, and I'll move my code over here. So for chapter 3, we're going to make a new file. We're going to call this 3.10.1 .Coral. Obviously, code does not have Coral built in, but I'm going to put this in here, and I'm actually just going to put this back as the original. Well, you know what? Let's rename this to -1. All right, and then let's take out all of that, all of this. Whoa. Let's take that out. Let's do, we're just going to do put frequency to output. This is cool. This is something I like about code, because we can come in here and just do this times, it already, because even though it doesn't know it's a function, it already has raised to power up here, and code does this. And let me put, my son was getting pretty fussy. So yeah, I like, man, for whatever reason, I don't know, it's like he's in the other room. I can't hear him that well, but the mic picks it up incredibly well. So if we just do in here R1, 2, and we can just type like that. So this, you know, it saves a lot of time, because it's just looking at what else is in the file, and it's allowing you to use the complete in those. Anything you've typed before, which is pretty handy. And then we do need one more, right? Alright, so this was the, oops, I screwed that up. Oh well, this will be the first file. And then we will just make a new file, call this 3.10.1.-1.coral. And in here we're gonna, oh yeah, that's right. This one doesn't actually, we don't need this, did we? So, Control S, alright. And then I'm going to grab this, put it here, put our integer steps, and then we're going to come here, we're going to do for steps equals 0, steps is less than 5, steps equals steps plus 1, and we do put frequency times raised to power r comma steps to output, and then in the event that steps, or when, so during this whole thing, if steps is not equal to 4, then we're going to put a space to output. Alright, so that is our file, and now what we're going to do is we will convert this to a, we don't need that anymore. So now we're going to convert this to a, oops, let's split this right. We're going to do a new file here. We're going to call this 3.10.1.py. Okay, and we've got that going on over here. Close that for now. Now, we need to get all this same stuff into Python. Python, we don't have to declare our floats, our frequencies, etc., etc. We can do r equals, and instead of r caret 2, oops, caret 1.0 to the 12 divided by 12. In Python, we don't do raised to power, we just do 2 of these. This means 2 to the power of. And we can do 1/12 here. And the cool thing about that is that if we show this, what we're going to do is get that is going to show up. 2 to the power of 1/12. It automatically does the float math for us. Now, what we could do here is we could do 1 times that, and if we were to run this, I guess not. I thought that that would work. Just doing 440. Why is R? Oh, yeah, we have to do that to the nth power. That's right. So, oops. So R equals this. Now, if we do frequency equals, and then we do R to the first power, right, frequency, we get that same thing when we don't have anything, but if we do here, frequency times R to the first power, right, frequency Now we get an error because frequency is not defined. We're using the undefined one here. But if we set frequency to equal 440, and now we run this again. 2 to the 1/12 is what I'm showing there. Frequency times. It should be doing this exponent, you know, first. Why am I getting a weird number here? R is equal to 2 to the 1/12 power. Do I need to put this in parentheses? Oh, I do. It's doing 2 to the 1 first. I'm an idiot. This one we don't actually have to put into parentheses. And there we go. So that's showing one step away. That's okay. That's what was screwing me up. My brain knew that this number should have been showing up, but it wasn't, and so then I was like, oh, well, then it must be because of, you know, I don't know. This should be a constant, essentially. That should be a constant, unchanging value, no matter where you go. If you multiply the current frequency by this, it should give you the next key, and if you multiply it by the negative of this, it should give you the previous key. Right, so we can do this, and we can start at this value. Ooh boy, we can do frequency equals, and we can just do 466.13761 615 180899. Let's try and see what happens when we do this. It should give us, oh, I'm printing R still. If we print frequency, this should allow us to get that 440, 439.96 math, float math. Fast, not 100% precise. Anyway, now that's all good and well. So we could do something like frequency equals, and then we can just do input. Please enter a base frequency. And then take that frequency, and we could do something like, well, this math isn't going to work. We're going to need to, first of all, turn all of this into a float. Then the math would work. And that will allow us to then, first of all, we can just print frequency, but we need, like, you know, pluses in here and stuff, so it would have to be print frequency plus frequency times R to the 1. Now, will it actually, I'm not actually sure if that'll work, but let's see. Is that just going to output them right next to each other if it even works? Oops. Please enter our base frequency. We're going to enter 440. So it's just adding them, right? Because we're not actually. So what we have to do here is we would have to do like string frequency plus, and then do a space plus, and do string. Turn this into a string, and then do this. Oops. Plus this. Plus, and do a string frequency times r to the second plus, right? You can kind of see where this is going. String frequency times r to the third plus plus string frequency times r to the fourth. All right. Let's see if we typed all that properly. Invalid syntax. Print string. Oh. I've got, what do I have? One too many here? Probably have one too many. I probably typed another one when it had already auto-completed it. Let's try that out. Okay. And then we get our spaces and everything looks exactly like it should. So that is one way to do it. And in my opinion, this would be kind of like the first way that we did it. And I think maybe instead we should use a loop in here. So maybe we just store all of these into an array. The way that I can think of to do this, I'm still new to Python. The way that I think of this working would be to make an array, and we'll call this frequency list, and then we'll make this into a list of, and we would do string frequency times r to the steps, 4 steps in range. We'll do 5. Did I get that? And then close the bracket there. So what this should do is take a string, do frequency times r to the steps power for each step in a range of 5. So starting from 0, going 0, 1, 2, 3, 4, 5, and then we should be able to print frequency list. Now I'm just doing this to see if we got the array set up properly. Enter base frequency 440. Sweet. Okay, we did, but now we got these annoying brackets and these annoying quotes afterwards because we've turned it into a string. And technically, I suppose we wouldn't necessarily maybe have to put it into a string. Let's see what happens when we set it as not a string. Now we just get the brackets, but because it's not a string, it's a float. So that works. But it gives us these brackets around it. And maybe we don't want the brackets, but we could do a join, do print, and do this dot join. and then in here put frequency list. Now this might do something weird because they're floats. Expected a string, yeah. So if we're going to use join, that's right. So if we're using join, frequency list right now is it's a list, and at the moment we can only join with strings, so that's why we would do the strings. I'm not actually sure. Can we strip that, or can we do a dot strip on there? I'm not sure. I have to Google this. Didn't give us an error. Now it gave us an error, and it says the list object doesn't have the ability to strip. Man, I cannot remember. Just curious whether this would. Can't remember what happens when we play around with these guys. Still gives us our brackets. I don't know how to get rid of the outer. I'm not sure how to get rid of the outer brackets just using the print, and we can't. I don't think I can use the format either. So let's go ahead and do this as a string. Why not? And I want to try something. I know that, so dot join. Yeah. I'm not going to mess with that. We're just going to do print, and then we're going to do a space dot join, and we're going to join frequency list together. This should do what we want it to do. 440, and there we go. We get this. So now if we were to do this, all we would have to do is change our range here. We could change this to 12. I'll do 13 just to make sure that it puts the 1 octave higher on there as well. We can click Python file, enter the base frequency of 440, and we go all the way up to 880, and we can run it again. Base frequency of 220, and we see we go up to 440. And so theoretically, if we want to go down an octave, we should be able to put that in there and do Python file and enter our base. Whoa. String frequency times for steps in range. Oh. So I would need to do 13. Wait. No. Oh, right. I would need to, if I'm going down, I would have to do times the negative steps. I believe that is what we would do to get our, let me see, it's not 220 because of the imperfect math, but it's basically 220, so negative steps instead of steps if we want to step it down. Because we're creating a list out of it, so you can't have like -1 spot. You have to put a negative value into the list. You can't have a -3 index. All right, so that worked. We have created this, and of course now we could do here, we could say steps equals, and we could just do input, enter how many notes you want to see. And this is probably going to give us an error because the math, and we want to see 5 notes. Oh, no, it didn't. But we still gave us the range here, so here we just have to do the range steps. Sorry. No. We have to name this something different, so we'll just do notes. Number of notes away. Put it in that range. Alright, now just do it again. That was a logic error. A couple of logic errors. 440, we want to see 5. Now we get our error because string object can't be interpreted as an integer. I think if we go here and we do int and then close our brackets, I think this will work. 440, we want to go 5, and that shows us our 5 notes. So we have the proper output that we want to see. It works. Cool. Neat. Done. Alright. So we've got our file with a bit of added functionality to it. Of course, if this, if we're going to be deploying this somewhere, we don't want people to be able to punch, anything else in, so we would need to do try and accept for these, for turning these inputs into floats and integers. But for now, just for the purposes of what we're doing, that'll work. This is kind of interesting to me. I love music, so I think I might want to try to play with some of this, like naming notes. We could name the notes. We could set up everything to where someone could say where do they want to start on the key on the piano, what note would they like to start at, what octave, and then display. Do they want to see the display in frequency? Do they want to play the note, or do they want to display the, could display the major scale, the minor scale, etc. I think I might just kind of move this over to PyPrac, to my PyPrac repository, my PyPractice repository, and play around with building some sort of musical app. First of all, I guess on the computer maybe, then put it onto, like a phone or whatever. Anyway, we'll see. Starting here, maybe port it to something else and do it that way. So that's it for now.